This is the second video in a two-part video series covering section 5.1 out of the OpenStax Calculus book, Volume 1. Section 5.1 addresses approximating the area under a curve. In the first video, we talked about the fact that we may want to know how much area is between a curve and the x-axis. When we do this, we can approximate that by using a rectangle and finding the area of the rectangle instead. Now, this is not a perfect method, but it will work somewhat to find the area under the curve. When we find the area under the curve, we're always talking about the area here between the x-axis and the curve. I'm having trouble coloring within the lines. So again, when we're looking at the area, we're talking about the area between the curve and the x-axis. You'll notice that up here I said between the values x equals 0 and x equals 2. If I didn't say that, then there would be far more area I would need to include. Let's take a look at how we might want to do this. This video is going to talk about Riemann sums. Riemann sums are named for Gerhard Riemann, who was a German mathematician who studied how to use different geometric shapes to approximate the area under a curve. We named 3 of them in his honor, although there are very many more Riemann sums that we could talk about. The 3 most common ones are the left Riemann sum, the right Riemann sum, and the midpoint Riemann sum. In the picture here on the left, you will see a left Riemann sum with 4 rectangles used to approximate the area of that function between 0 and 2. You may think now that I don't know how to count because you only see 3 rectangles and I definitely said 4. The problem with the left Riemann sum is that in this case, since the left endpoint has a y value of 0, this becomes what we would call a degenerate or trivial rectangle, where it is actually just sitting flat, like a flat piece of cardboard on the x-axis. It does have width. It's half a unit wide, but it has no height because its left endpoint, which I'll now put on here in red, the left endpoint has y value of 0. You'll notice that on here, the left endpoint is touching the function. The y value at the left endpoint then becomes the height of that rectangle. You can tell that when the function is going uphill or increasing, this means that I am short a lot of area. So it's an underestimation for an increasing function. On the other hand, when the function is decreasing or going downhill, it is an overestimation. I have too much area here on this side. I'll shade the too much area here in orange, and I'll shade the not enough area over here in green. That makes these not as good of an approximation. However, notice that in the picture on the right, I have changed it instead of 4 rectangles to 10. I still have my one degenerate rectangle sitting right here flat on the x-axis because the y value at 0 is 0. So that is a flat box which has width but has no height. Because there are 10 boxes, I could divide the region from 0 to 2 into 10 equal parts, and that will give me the width of each box. The height of each box is again given by the left endpoint, and you can see these touching the curve on the left side. You can tell that again, I am short area on the left where it's increasing, and I have too much area on the right where it's decreasing. However, if you shade the regions that are too much on the decreasing side, you can see that there's far less over amount than there was in the first picture. If we shade the underestimation on the increasing side, you can again tell that the green shaded area here where there are 10 rectangles is far less than the area here where there were 4 rectangles. In general, if you increase the number of rectangles, which decreases the width of each box, you get a better approximation. In this picture, I was using the left endpoint above here. In the next picture, I'm using the right endpoint. We would call this a right Riemann sum. The right Riemann sum, instead of using the left endpoint for the height of the box, is instead using the right endpoint. It just so happens that on this particular function, the right endpoint at 2 is also on the x-axis. So we again have a degenerate box sitting flat on the axis. When I increase the number of boxes to 10, it decreases the error in my estimation. You will notice, however, in both pictures that I am not completely accurate on the amount of area in the boxes compared with the area under the curve. However, the situation is reversed to the left Riemann sum. In a right Riemann sum, if it's increasing, I have an overage amount, and if it's decreasing, I have an underestimation. It was the reverse for the left Riemann sum. Let's take a look now at a midpoint Riemann sum. Here you see the graph of a midpoint Riemann sum for exactly the same function as before. In this case, we have sort of averaged our error on each individual rectangle. You can see that I am short a little bit and yet I'm over a little bit on the same rectangle. So if I again shade the overage amounts in orange, you can see that I am over with the 4 boxes for the part of the rectangle that extends above the picture. However, on each rectangle, I'm also short a small amount of area as well. However, compared to the previous ones, there's far less area that is in error than there was on the left Riemann sum and the right Riemann sum. In addition, because of the function that we used here, and because none of the midpoints cross the x-axis, we don't have any degenerate boxes that are sitting flat on the axis. When we increase the number of boxes to 10, you can see that the midpoint is actually providing a very good approximation for the area under the curve. If we used more boxes, we would get an even better approximation for the area under the curve. To find the area between the curve and the x-axis between the vertical lines x equal a and x equal b, you need to know how wide to make each rectangle. In general, we use the formula that delta x is equal to b minus a divided by n. In this case, delta x becomes the width of each box. Delta stands for change, and this means the change in the x values. This is the width of each rectangle. In this case, B is assumed to be to the right of A. That's the way we normally would write it. A is to the left and B is larger to the right. N is the number of rectangles you want to use. If this is the formula that you use to find your width, then you will find that every rectangle has the same width. When we use the same width for every rectangle, we call this a regular partition. Sort of like a regular solid has the same cross-section no matter where you slice it. A regular partition means every rectangle has the same width. This is not strictly required. We can do a Riemann sum where they all have different widths. If we let x sub 0 represent the left point of the interval where we're trying to find the area, A, then we can locate each endpoint of all the boxes by adding on to each of those values another delta x. Delta x will move us from one endpoint to another endpoint and all the way across. These sums are called Riemann sums. We use the y value of one of the x values in each partition as the height of the rectangle. The y value is, of course, the function value at that x coordinate. The three common ones are the three we've already seen: the left Riemann sum, the right Riemann sum, and the midpoint Riemann sum. Midpoints can be found with the formula you see here at the top. There is another formula for midpoints, which I will show you later on. This one just says, if you have a rectangle, add their 2 points together and divide by 2. In other words, average the 2 ends of the box, and that will get you the midpoint. Here's the formal definition for a left endpoint approximation. This is using a great deal more jargon, and you will see some i's minus 1 and sub i's. I minus 1 is the x endpoint before the ith one. So for example, if you were looking at your curve and you wanted to divide it up, you could do it in the following manner. Let's suppose that you had a curve that went like this, and here was your A, and here was your B. A is going to represent x naught. Let's suppose you want to make n boxes. The last one, of course, is going to be x sub n. Then you can divide up the axis into different sections, drawing different vertical lines. This one is x sub 1, then x2, x3, and so on. Somewhere out here in the middle, we have x sub I minus 1, and the one after it is x sub I. The one after that is x sub I plus 1. And then, of course, it keeps going until you finally get to B, which would be the nth one. We will construct rectangles with width delta x and height equivalent to whatever the function value is at the point we choose. For a left endpoint, it's always going to be the one on the left. This represents a Riemann sum giving you a left endpoint for n different boxes. This is the reason that we studied the sigma notation. It gets tedious when you have 42 boxes to have to write each one individually. By writing it with the sigma notation, I can indicate the sum of all 42 boxes with one formula. This is a picture of what the left endpoint looks like, and you can see here that they have labeled the different ones. Keep in mind that we do often change our subscripts from I to K to N. These are the typical letters that you will see used for subscripts. This is the rule for a right endpoint approximation. It's basically the same as the left endpoint, except that you don't use A. Just as in the picture for the left endpoints, you'll notice that we never used B as one of the heights of a rectangle because B is never the left endpoint of a rectangle. On the right Riemann sum, we do use B, but we do not use A because A is not a right endpoint. This summation notation is again just a shorthand way of writing the sum of all the rectangles to approximate the area under the curve. You can allow every rectangle to have a different width. If you do, we define the mesh, spelled M-E-S-H, to be the width of the widest rectangle. As long as the width of the mesh gets smaller and smaller, we will get a better and better approximation. We also can use a different point in every single rectangle to compute the height of the rectangle. When we do this, we might call it x sub I with an asterisk above it, or what's commonly known to mathematicians as x sub I star. You'll see here at the bottom 3 formulas to generate those points for the left Riemann sum, the right Riemann sum, and the midpoint Riemann sum. This is the second formula I told you about for finding the midpoint of an interval. These are all based on starting at the far left point of the interval, which is A. For a left Riemann sum, you will use A, and then you add on delta x. For the right Riemann sum, you never use A, you use the first A plus delta x, no matter what. The area under the curve is approximated by the sum of these rectangles. In other words, we can say that the area is approximately equal to the sum from I equal 1 to n of the function at x sub I star times delta x. Keep in mind that delta x represents the width of the rectangle, and the f of x sub I star represents the height of the rectangle. So that the area we have here is the height times the width, or length times width, whichever you prefer. As we increase the number of rectangles, the width of each rectangle will decrease and get smaller. This formula here gives you the sum for a Riemann sum. This is a generic formula where they're using f of x sub I star to represent any point inside each width where you're going to find the height of the box. If you allow the number of boxes to go to infinity, then the width of the boxes will start to approach 0. Now you can't really have an infinite number of boxes, and you can't actually allow the width of the box to be 0. If the width of the box is truly 0, 0 times any height is going to be 0. However, this is a limit, and the idea is you let it get very, very close. And if you do that, you get a better and better approximation of the area under the curve. This is the meaning of the last definition you see here at the bottom of the page. If the function is continuous and not negative, not going below the x-axis between a and b, then you can let f of x sub I star times delta x be the area of each rectangle. When you take the sum from I equal 1 to n, you're adding the area of every rectangle together. We call that a Riemann sum. By taking the limit as n goes to infinity, that means delta x is approaching 0, and this gives us not an approximation for the area, but the actual true area under the curve. The proof of this is beyond the scope of the course at this point. Provided that the mesh of the partition goes to 0, where the mesh is the widest of the uneven width boxes, then the limit of the Riemann sum will always equal the precise area under the curve. We're now ready to do some examples. We're going to actually work the example that I gave previously in the pictures. This is the function f of x equals x to the fourth minus 5x cubed plus 6x squared, and between the vertical lines x equals 0 and x equal 2. I want you to use a left Riemann sum and 4 rectangles. In other words, we're actually computing the area for the first picture we saw. Here's the picture that represents what we're trying to do. We're going to use the left endpoint to compute the height of each rectangle. I need to know what the width of the rectangles are first, so the first thing I do is find delta x. The formula is b minus a divided by the number of boxes. My b is 2, a is 0, and I want to use 4 boxes. 2 divided by 4 gives me a width for each box of 1/2. That means that my boxes, if I were to label them on a number line, are going to start at 0 and stop at 2. Halfway in between we have 1, but the first box will end at 1/2, the second will end at 1, the third will end at 3/2, and the fourth will end at 2. This makes the endpoints of my rectangles. The left endpoints, however, I'll mark with red arrows. That's a left endpoint for the first box. 1/2 is the left endpoint for the second box, 1 is the left endpoint for the third, and 3/2 is the left endpoint for the fourth box. Now I need to compute the heights at those left endpoints. To find the heights, I need to plug in the left endpoints to the function. F of 0 plugged into the function you see here will simply give me 0. F of 1/2 plugged into that function will give me 1/2 to the fourth minus 5 times 1/2 quantity cubed plus 6 times 1/2 squared. Take a moment to compute the value and then restart the video to see if you got what I got. Hopefully you got 15/16 or 0.9375. Let's now compute the remaining two heights for our third and fourth boxes. F of 1 will give me, looking back at the function, 1 to the fourth minus 5 times 1 cubed plus 6 times 1 squared. That's going to give me 1 minus 5 plus 6, which should give me 2. When I plug in f of 3/2, it'll require a little bit more work. You may want to grab a calculator again to compute this value, then check to see if your answer matches mine. I got 51/16 for the value of the function when x is 3/2. That will give me the tops of the rectangles. Now it's simply a matter of adding them together. Since there are only 4, I don't have to mess too much with the function notation, or rather with the sigma notation. I can simply add together all of my boxes. Since I have each box being 1/2 wide, I will take the width of the box and multiply by the height of the box. So my area is about 1/2 times 0, the height of my degenerate box, which is sitting flat on the x-axis, plus 1/2 times the box that has height at 1/2, which is 15/16, plus 1/2 times the box where the height at x equal 1 is 2, plus 1/2 times the height of the box when x equal 3/2, which was 51/16. Notice that the 1/2 is constant on each term, which means I could also have factored out the width and then simply added together all the heights. 0 plus 15/16 plus 2 plus 51/16. Take a moment to compute that value. I got 49/8 for the sum of the y values times 1/2 gives me 49/16, which is 3.0625. Let's repeat the process now, but use instead 10 boxes. Go ahead and pause the video, make your calculations, then turn the video on to compare your result to mine. In the interest of time, I've produced a table for you down here, which represents the left endpoints for a 10 rectangle partition of the interval from 0 to 2. I've also given you the y values at those left endpoints in a decimal notation, since the fractions get a little unwieldy. Again, notice that I've divided up the interval into the 10 equal boxes. The only ones that serve as left endpoints, however, are the ones on the left. That's a box there. That's a box there. This is a left endpoint for that box. That's a left endpoint for that box. This is a left endpoint for, oops, got a little wide there, that box, and so on, right until I get to the second to the last. The second to the last value, 1.8, is the last left endpoint. The last box does not have a left endpoint at the right endpoint of the interval, which is 2. Now we need to compute the area of each box. Since the width of each box is 0.2, We will multiply each of these values by 0.2 and add them together. Conversely, you could also add these all together and then multiply by 0.2. Pause the video again, do the multiplication, and see if your answer matches mine. When I did the calculation, I got approximately 2.38656. This is an approximation for the area under the curve between it and the x-axis. Notice that this is less than what I got with the 4 boxes above. When I did 4 rectangles, I got an approximate value of about 3.0625. This time I got a smaller approximation, but it should be more accurate because I used more boxes, which have less error involved. Let's do the same thing for the same function, but let's now use a right Riemann sum. Here's the picture we had before of what the right Riemann sum looks like, where it is the right endpoint of each partition that becomes the height of the rectangle. That does give us one degenerate flat on the line box on the far right. Remember that we can find the width of each box in a regular partition where they're all the same width by taking the difference in the values of the interval and dividing by the number of boxes. This gave us a width of 1/2. It will be the same here for the right Riemann sum. However, when we divide up our interval from 0 to 2, we will instead be taking the right endpoint to serve as the height of the box. That means instead that it is 1/2 that is the first endpoint of the box, then 1, then 3/2, then 2. We will not use 0 as the height of any of our boxes. Now that we have our x coordinates for the ends of the boxes, we need to compute the y values at those right endpoints. However, we've already done the work for 1/2, for 1, and for 3/2. The only one that is new to us is at 2. Let's take a look up above and see if we can remember what those values were. At 1/2, we found that the value was 15/16, and at 1, the value was 2. We also got the value at 3/2, which I believe was 51/16, but let's go check to be sure. We scroll back up, we see that yes, indeed, the function value at 3/2 was 51/16. That only leaves us one that we actually have to compute. That leaves us only f of 2 left to compute. That will give us 2 to the 4th minus 5 times 2 cubed plus 6 times 2 squared. 2 to the 4th is 16. 2 to the 3rd is 8. 5 times 8 will be 40. 2 squared is 4, and 6 times 4 will give us 24. That means that the y value when x is 2 is again 0, which makes sense since it's sitting right on the x-axis. Now we need to compute the approximate area between the curve and the x-axis by adding up the area of our 4 boxes, including our degenerate box, which has no area. So the area is going to be approximately equal to the sum of the area of each box. Each box would have a width of 1/2 times the height. Box 1 has height 15/16. Box 2 has height 2. Box 3 has height 51/16. And box 4 has 0 height because it's degenerate and flat on the line. Take a moment to compute your result. I got 49/16. 49/16 multiplied out will give us about 3.0625. How does that compare with what we got for the left Riemann sum? Scrolling up to the left Riemann sum, I got exactly the same value. Do you think that's normal? The answer is no, that is not normal. Normally, the left Riemann sum and the right Riemann sum are different. Why in this case are they the same? Let's look back at the graph to see why we think they might be giving us the same. The problem with the graph and the reason the left Riemann sum and the right Riemann sum are giving us the same value is because the graph is symmetric across the interval from 0 to 2. That is why we are getting the same value with the left and the right Riemann sums. That normally will not be the case. In the interest of time, we won't repeat this one with 10 rectangles, but we do want to try at least one midpoint Riemann sum. In this example, we're going to take the same function over the same interval, and we're going to also use 4 rectangles, but we're going to use a midpoint Riemann sum instead. The midpoint Riemann sum is generally more accurate than the left or the right Riemann sum, but it does require a little bit more work to get the values at which you want to compute the height of each rectangle. Let's go ahead and find again the width of each rectangle. The width is given by delta x, which is going to be b minus a divided by the number of boxes. As it has been previously, this is going to give us the value of 1/2. Now, however, when I divide up my intervals between 0 and 2, I need to split it up into the 4 boxes. That will give me a box between 0 and 1/2, a box between 1/2 and 1, a box between 1 and 3/2, and a box between 3/2 and 2. To get the midpoint, however, I need to find the average of the 2 endpoints of each box. If I average 0 and 1/2, I find that the first midpoint is 1/4. Averaging 1/2 and 1 would give me a midpoint of 3/4 or 0.75. Averaging between 1 and 1.5, I would get 1.25 or 5/4. And averaging between 3/2 and 2, I would get 7/4, not halves, but fourths. That gives me the midpoints of each box. Realize that the rectangles are extending across, but we're finding the height at the midpoint. The midpoint will give us the height of the box. There are the 4 rectangles, and 1/2, 3/4, 5/4, and 7/4 form the midpoints of each box. You can use either the first method or the second method to compute the midpoints. Now we need to find the value of the function at those midpoints. Go ahead and pause the video here and compute your values, then turn it back on to compare them to mine. When you have completed the calculations, hopefully you got something relatively close to mine. It's possible I made an error here or there. When you add these up and then multiply by the width, you'll get something that's about 3.8. Keeping in mind that these are only approximations, notice that the approximations for 4 rectangles were very different from the approximation for 10 rectangles. The approximation for 10 rectangles was more like 2.38656. The actual value of the area under the curve, found by means that we will learn next week when we learn integration, is actually 2.4, which means that even with only 10 rectangles, I got extremely close to the actual area under the curve. The area under the curve, again, was exactly 2.4 square units. We'll be able to find that using techniques called integration, which is the reverse of differentiation. Now I would like to show you, using Desmos, what it looks like on the actual function to create different numbers of boxes and approximate the area under the curve with Riemann sums. This is a blow-up of the same function that we've been working with throughout this entire video. This is a right Riemann sum, as you'll see, since it is the right endpoint of each rectangle that touches the curve and the function f of x. The function is given here. You'll notice that I've set my slider bars to be at a equals 0 and b equal 2. If I change the number of boxes, watch what happens to the area under the curve and whether it gets better or worse. If I increase the number of boxes, I'm now up to 42 boxes. It's beginning to be a very close approximation. If I increase even more, say to 100 boxes, it looks extremely good. If you go all the way up to 200, you can't hardly tell that that is in fact an approximation and not the exact area under the curve. Again, you can scroll all the way back down where we were, which was at 4 or 5 or even lower. You could do 3 boxes. This is what it looks like when you're trying to approximate using a right Riemann sum. Let's take a look now at the left Riemann sum. Here's the same curve with the same function, the same left endpoint and same right endpoint. You can see, however, that these must be left Riemann sums because it's the left corner of each rectangle that is touching the function. If I take my slider bar for the number of boxes and I increase it, watch how the area under the curve gets closer and closer to the true area. This particular mean goes all the way up to 500 boxes, at which point you cannot see that it is not in fact the precise area under the curve. However, as you decrease the number of boxes, you begin to notice the area. You can again take it all the way down to where we were at 4. Let's take a look finally at the midpoint Riemann sum. Here is our same curve that we're looking at, but now you can tell that this must be a midpoint Riemann sum since it is the center point of each rectangle that intersects and touches the function. If I take the slider bar for the number of boxes and increase it, it very quickly becomes a very good approximation. This one also goes up to 500. But by the time you get to 350, you can hardly see the difference. Again, you can scroll all the way back down to where we were, which was closer and in between 4 and 10. One of the last things I want to show to you is that you can actually take any function you want and you can use these applications on Desmos to look at different functions. You can change the function by changing it here. You can also change the values over which you want to find the area under the curve. If you do that, notice what happens when it dips below the axis. Do you see that this area down here is now red? As you might expect, we do have what's called signed area. As the area goes below the axis, we consider it to be, quote, negative area. If you increase the number of boxes now, you'll see that it does the same thing it did before, but in all the various regions. This is something we will continue to study as we progress through Chapter 5 in our examination of integration. This is the end of this video over Section 5.1, Approximating the Area under a Curve.